In this second half of chapter 3, we're going to talk about projectile motion and relative velocity, both places where we need to apply what we've just learned about vectors. First of all, what is a projectile? A projectile is anything that you can launch. And then after you launch it, it's going to follow a path that's determined by gravity. In other words, after you throw it, shoot it from a gun, fire it from a cannon, the only force that's acting on it is gravity. Now, the person who figured this out for us was Galileo. What he discovered is that we can treat vertical and horizontal motion separately. Horizontal, we're usually thinking X. We can treat them completely independently. The speed that you're going horizontally won't affect the way that you're falling. In fact, the vertical aspect of projectile motion is identical to free fall. It's exactly like free fall. Vertically, you've got an acceleration of negative 9.80 meters per second squared. Horizontally, there's no acceleration, because when we do projectile motion, we're assuming there's no other forces, so we don't have to worry about air resistance slowing us down horizontally. We don't have to worry about winds that might be speeding us up horizontally. Horizontally, we're going to travel at a constant velocity. Okay. Vertically, we're going to be accelerating due to gravity, but horizontally, we'll be moving constant. There's basically two types of problems. The easier problems are when something is launched horizontally. If we launch a vector horizontally, it looks like this. Horizontal and by that I mean that I'm launching it with a horizontal velocity. So we can picture something picture a ball, it starts off with an initial velocity that's horizontal. But of course, as soon as we launch it, gravity kicks in and it's going to accelerate down and have a path that looks something like this. Now, in order to have a horizontal projectile, it has to start off with some initial height here. You have to throw a baseball above ground. You can't have a horizontal projectile start off at ground level. If we think about everything that's going on, horizontal motion, the acceleration is 0. The velocity is just whatever your initial velocity was. And your initial position, we usually let that be 0 as well. That's what's going on. That's our initial conditions, if you want to think about it. Vertically, the acceleration is negative 9.80 meters per second squared because we do have gravity. The initial velocity in the y direction is 0 because we did launch it horizontally. We did not launch it up or down or at any angle. And the initial height is y0. If we look at our formulas, we get some interesting things. Because we have quite a few things that are zeros, our formulas tend to simplify pretty quickly. In particular, our formula x equals x0 plus v0t plus 1/2 at squared. Remember, these are constant acceleration, but if the acceleration is 0, that goes away. if x0 is 0, and we just get that x can be found using this very simple in other words, our horizontal position is just our horizontal speed times the time. If you launch something horizontally at 10 meters per second and you wait 3 seconds, it's going to have traveled 30 meters. If you launch it at 50 meters per second and you wait 3 seconds, it's going to have traveled 150 meters. But it's just going to move at a constant horizontal speed. It's not going to slow down. It's not going to speed up. We do the same thing over here, only this is going to be constant. Velocity will be constant. Vertical velocity is not constant because we have an acceleration. So our vertical velocity is v0 plus at. Well, that's always 0. So this is going to be, the vertical velocity is just negative 9.80 t. So after 1 second, it's going to have a downward speed of negative 9.80. Its horizontal speed is going to be whatever the horizontal speed was at the beginning of the problem. Okay. If we do y equals y0 plus v0 yt plus 1/2 at squared, we see that this is going to be whatever our height is plus or minus 4.9 t squared. That's our height. That's 1/2 our acceleration due to gravity. Those are the problems the equations that we need. There's really not that many. One thing we want to think about is what determines how long a projectile motion lasts. And if you stop and think about it, the time in the air depends totally on the vertical motion, regardless of whether it's horizontal or whether it's launched at some other angle. How long it's in the air is just going to be how long does it take to hit the ground. And it hits the ground because it's falling. It's always a vertical problem. One other thing I want to talk about before we work an example is I just want to convince you that you can treat horizontal and vertical motion independently. And one of the ways you can think about it is assume that, and this is East Texas, so I'll use a gun example. Suppose this is a gun right there, and in my other hand I have just a bullet. And if I drop a bullet and fire the gun horizontally, perfectly horizontally at the same time, what I'm telling you is that the bullet that's fired is dropping at the same rate that the bullets that dropped. Now, there's a whole lot of people that think the bullet that you drop ought to hit the ground first. But let's think about it. If I shoot the gun up and drop a bullet at the same time, everybody's sure that the bullet that I drop hits first, and they'd be right. But if I fire the gun down and I drop the bullet at the same time, everybody's sure that the bullet out of the gun hits the ground first. Even if it's just a little bit above horizontal, we still think that the dropped bullet hits the ground first. Even if it's a little bit below horizontal, we think the gun from the bullet hits first. So it makes sense that if I shoot perfectly horizontally, that horizontal bullet is falling at the same rate as that dropped bullet. We can do it completely independently. Okay, so this is our general approach. A lot of times we'll start with the vertical motion because we're trying to find time. Now, that might be different if we know already how far it travels. And let me point out, this is generally x. It's also called the range. How far does the object travel? This is y0, and it's obviously the height. So we've got our approach. Let's work an example. motorcycle speeds off a cliff .0 meters high at 25.0 meters per second. How far from the base of the cliff does he land? Can't hurt to have a picture. So here's a cliff. We know this cliff is 75 meters high. Here's our motorcycle. There's somebody on it. And it's going to go flying off at 75 meters per second. That's going to be horizontal because you don't drive a motorcycle. He's not driving up the cliff and launching or driving down a hill. It's a perfectly horizontal. Whoops, that's 25, sorry. So we know a lot of stuff. I could write down everything that we know. I know that horizontally, acceleration is 0, initial velocity is 25, initial position is 0. I know that vertically, the acceleration is negative 9.8. The initial velocity, v0y, is 0. A lot of times students mess up and they want to put 25 meters here. But he doesn't have an up and down velocity initially. He only starts off with a vertical. Now he's going to do this. He's going to accelerate, and you're going to get that shape right there. That's a parabola. We're interested in that distance. How far does he travel? His initial height, 75.0 meters. In order to figure out how far he travels horizontally, I need to know his speed and I need to know the time. Well, I know his speed. He's going 25 meters per second. What I don't know is how long he's in the air. But that's determined by his height. If you know how high something is, you have enough information to determine how long it takes something to fall from that height. So I'm going to start with y equals y0 plus v0 yt plus 1/2 at squared. That's my standard equation. But when I fill it in, I want my final height y to be 0. He started with a height of 75. He had no initial velocity, so that's going to be 0. And then 1/2 the acceleration is negative 4.9 t squared. So actually a really easy equation to solve. When does 4.9 t squared equal 75? So I use a calculator. 75 divided by 4.9. Take the square root. And it takes about 3.91 seconds. We have 3 significant digits, so I'll keep 3. They didn't ask for that, but it's always a good intermediate thing to find out. Now, how far did he travel? Well, if we put in x equals x0, the initial velocity in the x direction times time plus 1/2 at squared. This is very important. This is acceleration in the x direction. In the x direction, the acceleration is 0. This is 0. This whole equation, that goes away, comes out to be that x is equal to v0x times t. So he was going 25 meters per second for 3.91 seconds. comes out to be 97.8 meters. Okay, pretty basic problem. We dealt with the time because we didn't know the time first. Okay, once we knew how long, it was easy to figure out how far. Generally, if the projectile is launched at horizontal, it's a little bit easier problem. Okay, the other type occur when we have projectiles that are launched at an angle. Now, when we launch something at an angle, we might launch it from ground level, like if we're kicking a football, but we might launch it much higher, like if we're shooting a free throw. Okay, so it's possible that that height will vary. Might be on the ground, might not be. We're going to look at one where we're starting where it looks like we're on the ground. Here's the ground. What happens if you say you kick a football with some initial velocity at some angle? It's going to form a parabola too, only you're going to see a whole parabola. Whereas with a horizontal projectile, you're starting at the top and only saw half of a parabola. The first thing, the very first thing, and the step that too often students forget to do, is you need to take that initial velocity and break it into horizontal and vertical components, because we have to treat horizontal motion and vertical motion separately. There won't be a horizontal acceleration, so once we get that horizontal component, that will be our constant horizontal velocity. But there will be a vertical component. Okay? That vertical velocity will be changing throughout the problem because of the acceleration due to gravity. How do we get components? Well, v0x is just the initial velocity times cosine theta. We just get a component, a vector component. v0y is v0 sine theta. Pretty much everything else is just like what we said before, not that different, but that's important. So horizontally, acceleration is 0. The initial velocity is v0 cosine theta. Last time the initial velocity was the initial velocity, there weren't any components. And we can still let x0 equal 0. So that's pretty easy. We just have to remember we need a component of the velocity. Vertically, the acceleration is negative 9.80 meters per second squared. The initial velocity vertically is v0 sine theta. And again, our initial is the height. That could be 0, but that could be somebody standing up on a ladder launching something at an angle. Our equations are very, very similar. We've just got this factoring right here. So let's look at a problem. Let's let somebody kick a football with an initial velocity v0 is 20 meters per second at an angle of 37 degrees. So we're kicking it 37 degrees above horizontal. Very first thing you need to do is figure out what is the x component. It's 20 cosine 37 degrees. Okay, what is 20 cosine 37 degrees? Comes out to be 15.97. Really, really close. That's really the only piece of horizontal information that we need. We know the acceleration is 0. We know horizontally we're going to let it start at 0. If we drew a picture, it'd be here's the football, just like that. Okay. Vertically, so that's my horizontal. The initial velocity, v0y, is 20 sine 37. I do 20 sine 37. Comes out to be about 12.04. That makes sense. We're kicking at 37 degrees. We're kicking it more horizontal than we are vertically. All right, let's see what we can figure out. Let's see if we can figure out how far the ball travels, how long it's in the air, perhaps what its maximum height is, when that maximum height happens. All right, let's start with how long it's in the air. We know that vertical motion determines the time, so I'm going to say y equals y0 v0 yt plus 1/2 acceleration in the y direction t squared. I put that there because I want you to remember, if we're talking y, we have an acceleration. If we're talking x, we don't. So we started at a height of 0, and we're going to land at a height of 0. If we're kicking a football off the ground, and we're just going to wait till it hits the ground. This is 12.04 t minus 4.9 t squared. Not too bad. We can solve this pretty easily. We can solve it by factoring. We can take out a t. Notice one of our solutions is t equals 0. That makes sense. The ball was on the ground. We're asking the question, at what time has the ball hit the ground? Well, the ball was on the ground at t equals 0. I do 12.04 divided by 4.9. And to 3 significant digits, well, I'll tell you what, let's write it. If we just wanted to find the time for other problems, it's 2.457. If we're rounding everything to 3 significant digits, then the time in the air is 2.46. I'm going to write that over here. Time is 2.457 seconds. Like I said, if it was our final answer, I'd go with 3 significant digits, 2.46. While we're talking about rounding in significant digits, I'm going to round all of my angle measurements to the nearest degree. I'm not going to worry about tenths of degrees, fractions of degrees. When we're doing the part with angles, and there's a couple of reasons for this, but mostly for simplicity, we're going to round angle measurements to a whole number of degrees, no matter what the rest of the problem looks like. Okay, so we know how long it's in the air. How far did it travel? Well, how far it traveled is just this. Remember, x0 is 0, there's no acceleration. Horizontally, it's just distance equals rate times time. So 15.97 meters per second, 2.457 seconds. To 3 significant digits, it's 39.2 meters. So we know how far it traveled. There's some other questions that we could answer. We can answer the question, how high did it go? When was it at its maximum height? That requires us to remember something about the maximum height. When you kick a football or you throw something up, this is really a vertical motion problem. At the very top, right here, the y velocity is 0 because it's going from rising to falling. Now the x velocity is still v0x. So it hasn't stopped. In fact, it's got a perfectly horizontal velocity right there. But at the very top of the path, the vertical motion or the vertical velocity will be 0 because it's changing from rising to falling. So if I want to know the time to reach the maximum height, I just use v equal v0 plus at, but I do it for just the vertical, just the y. So 0. Initially, it was going 12.04 minus 9.80t. I just have to solve that for t. And I think you're going to see that the answer is perfectly reasonable. 12.04 divided by 9.80. I get 1.229. You'll notice I get half of that. Well, that makes sense. If the whole trip is 2.46 seconds, then this ought to be 1.23 seconds. Remember, if we round this to 3 significant digits, we're going to agree perfectly. The time for the first half of the trip and the time for the second half of the trip should be the same. The time, if something is launched and lands at the same height, the time it takes for it to go up and the time it takes for it to fall down are exactly the same. If you launch it and catch it at the same height, or it launches and lands at the same height, that motion is going to be symmetric. So we know it took 1.229 seconds to get to its maximum height. So we can actually calculate the maximum height. So I don't want to round it too much too early. So I just need to know what is the height. Same equation at that time. Well, that was 0. This is 12.04. We're going to put in 1.229 for the time minus 4.9, 1.229 squared. We'll see how high our football went. Into 3 significant digits, it came out to be 7.40 meters. So that was our maximum height. So we found the distance it traveled, we found out how high it went, we found out how long it was in the air. We pretty much, if we know initial conditions for a projectile, we know exactly what will happen afterwards. Okay, let's do one more problem. This one's more challenging. And then we'll do, let's see. This time we're going to kick our football just like before. And we're even going to have the same initial velocity. We're going to start V0 is 20 meters per second. And it's at an angle of 37 degrees. But There's more to it. We are 36.0 meters from the goalpost that has a crossbar that is 3 meters high. If we kick it perfectly centered, the question is, will it go over the goalpost? Let's draw a picture of our problem. So here's the goalpost. It's 3 meters high right here. Looks like that, but we're interested in the fact that it's got to clear that post. It's launched at 20 meters per second. And this distance from here to here, 36 meters. Okay, we just have to think about everything we know and everything that we can figure out with what we know. We know that the initial velocity in the x direction was 15.97. We know the initial velocity in the y direction was 12.04. But we know something we didn't know before. We know where it lands. If we start this time, this is one of the times where we can work backwards and we can figure out how long a time period we're interested in. We're really only interested in what happens from here to here. And what I need to know is, how high is it when x is 36 meters? Is it above 3 meters so it'll clear the goalpost? Is it below 3 meters so it can't clear the goalpost? If we think about it, we can figure out the time by looking at the time to travel 36 meters. We know x equals v0x times t, and it has to travel 36 meters. It's traveling at 15.97. So the time required is going to be 2.254 seconds. That looks like that. That's the time. That's what we're interested in. So at t equals 2.254 seconds. All right. I just need to know how high it is. How high will it be at that particular moment? I'm asking a vertical question now. I'm asking how high it will be. Well, it started, I want to know why. It started at the ground. The initial velocity, 12.04. Time is 2.254. 1/2 of the acceleration is negative 4.9. Remember, the acceleration here is negative 9.8. And then that same time, 2.254 squared. I'm squeezing it in on the board there. Comes out to be 2.24 meters. Which means what? It's too low. You can't kick the football from 36 meters away at that angle and have it clear the goalpost. It won't clear it. So that asks another question. Okay, if that's too low, we know we're too far away. At what height? How close? What's the minimum distance in order to be successful? How close will I need to be in order to be successful? That's going to change this question. That time, if we want to change the question, let's go back to here and say, let's figure out the time we need. I need this to be 3. I know that's 0. 12.04 t minus 4.9 t squared. And again, I kind of like this one because it factors, well, it won't factor because I have to subtract the 3 over. So I know I get this equation. When I solve this equation, and I can solve it by putting it in y equals, put this in y equals, put y2 is 0, find where that intersects, find the solution to this quadratic. I can solve it and I get 2 answers. One is t equals 0.281, and the other is t equals 2.176. Nope. Yes. Okay. Why do I get 2 times? Well, if you think about what happens, there's 2 times where it's 3 meters above. Once way over here, and another time way over here. You're going to be really close to the goalpost if you hit there. But this means we actually get a range of distances that work. Any time after 0.281 seconds will be close enough until 2.176. So we can put those both in and get a range. By putting 15.97 times 0.281, that gives me 4.5 meters. So if I'm 4.5 meters, I'm really close to the goalpost, I'll get it in. If I put in 15.97 times 2.176, I get a distance of 34.7 meters. There's my range. At 36 meters, he was just a little too far away. 34.7, that's the maximum distance from the goalpost that he can be and be successful. 4.5 is the minimum, but anywhere between 4.5 and 34.7, you can see from here to here, he's going to successfully make that goal. All right, let's look at relative velocity. Suppose that I have a train. The train travels 25 meters per second east. And we don't usually have to mention this, but I need to mention it for this problem, relative to Earth. Most of the time when we say how fast something's going, we're thinking relative to the Earth, but not always. A passenger walks to the front of the plane or train, and that passenger is going 3 meters per second. Now we know that person isn't going 3 meters per second relative to the Earth. That person's going 3 meters per second relative to the train. If I ask you how fast that person was going relative to the Earth, most of you wouldn't have any trouble in visualizing it. If somebody's outside and this is a glass train and we can look inside, they see that that person is going 28 meters per second to the east relative to the earth. How does that work? The velocity of the passenger relative to the earth, and that's what that means. Passenger relative to the earth is equal to the velocity of the passenger relative to the train plus the velocity of the train relative to the earth. Notice how if you want this to this, you've got this intermediate. It's on the bottom here, it's on the top there. In this case, it's really simple. The passenger relative to the train was 3 meters per second. The train relative to the earth was 25 meters per second. And we get 28 meters per second. Okay. First train is going 25 meters per second relative to the earth. Going east, about that. What if I have a second train? The second train is going 35 meters per second west relative to the earth. If these two trains are on the same track, heading directly towards one another, what is their relative velocity? We have the first train going like this at 25 meters per second. The second train is going like this at 35 meters per second. Let's get the velocity of the first train relative to the second train. I want the velocity of train 1 relative to train 2. Well, think about that. I know the velocity of train 1 relative to the earth. I'm going to need the velocity of the earth relative to train 2. This is where it gets a little tricky. If I know this relative to the earth, then I need the velocity of the earth relative to train 2. Well, this is 25 meters per second. "35 meters per second west is negative 35 meters per second. So let's write all these down. Train 1 relative to the earth is 25. Train 2 relative to the earth is negative 35. And that just indicates direction. If this is a positive 25 meters per second because it's going to the east, then train 2 has a negative 35 meters per second because it's going to the west. If the velocity of train 2 relative to the earth is negative 35, then the velocity of the earth relative to train 2 is positive 35. Remember, all motion is relative. If we treat it like train 2 is stationary and the earth is moving underneath it, then the earth would be moving underneath it to the east. If the earth is still, the train is going west. But if we think the train is still, then the earth must be going east. Plus 35 meters per second is 60 meters per second. A lot of you didn't need that much work. You know, if once they're headed towards each other, one's going 25 meters per second, the other one's going 35 meters per second, they're closing that gap at 60 meters per second. So if you're in train 2, it appears as if train 1 is coming directly at you at 60 meters per second. If you're in train 2 and you consider yourself the at-rest frame of reference, then train 1 is coming at you at 60 meters per second. Alright, it gets a little bit more confusing in 2 dimensions, but really it's just a matter of adding vectors. Suppose a boat travels east across a river at 8 meters per second relative to the water. In other words, if it was in still water, the water wasn't moving, he'd be traveling 8 meters per second. However, the water is moving. The river's current is 6 meters per second south relative to the shore. And we want to find the boat's velocity relative to the shore. I want the boat's velocity relative to the shore. Well, the velocity of the boat relative to the shore is going to be the velocity of the boat relative to the water plus the velocity of the water relative to the shore. I know what those vectors are. I can draw a picture. I'm going to have to add these 2 vectors. I have a vector. This vector is 8 meters per second to the east, and this vector is 6 meters per second to the south. If we were thinking in terms of components, this is a positive 8. This is actually a negative 6 because it's pointing down. They would be perpendicular. All I have to do is add perpendicular vectors. It's the Pythagorean theorem. So the size of the velocities would be the square root 8 squared, negative 6 squared, 10 meters per second. If I want to know this angle, I'm going to have to do a tangent inverse. My x component is positive 8. My y component is negative 6. So that's going to I'm not going to have to add 180 because x is positive. That's going to be quadrant 4. X is positive, y is negative. So tangent inverse of negative 6 over 8 comes out to be negative 37 degrees. In other words, this angle right here is 37 degrees. If I wanted to write that with some direction, it's not true east. The boat would be sailing 10 meters per second at 37 degrees south of east. Do one more. Let's suppose that a plane is traveling 450 kilometers per hour at 30 degrees north of east relative to still air. It's going 450 kilometers per hour at 30 degrees. It's north of east. So if we wanted to draw this in a coordinate plane, it's going something like this. There's east, there's north. All right, as long as the wind doesn't blow, that's its course. But suppose we have an average wind, an average sustained wind of 40 kilometers per hour. At 45 degrees north of west. That's basically true northwest. Okay. 45 degrees north of west. We need to picture another horizontal. There's another horizontal. There's our coordinate plane. Picture coordinate plane right there. It's going off this way. 40 kilometers per hour. We can see, and I'll probably do it a little too big, let's shorten that up. We can see that that wind is going to blow our plane off course. It's going to change the velocity of the wind, of the plane. So that we end up getting a resultant slightly off. All right, let's think about this. Let's see if we can find the velocity of the plane relative to the Earth. Okay, and this wind is measured relative to the Earth. That's going to be the velocity of the plane relative to the air plus the velocity of the air relative to the Earth. I'm going to have to add those two vectors, but I have those two vectors. How do I add vectors? I go back to what we did in the video over vectors. I'd say, okay, the x component is going to be 450 cosine 30 degrees plus 40 kilometers cosine, I need to know what angle 45 degrees north of west is if I measure it from the positive x-axis. Well, if I go from here to here, that's going to be 90 plus 45. That's going to be 135 degrees. I hope you can see that. If we picture it, I'll draw a little separate picture just to help you see it. If it's going 45 degrees this way, that's 45 degrees north of west. Here's west. Here's north. I need this angle measured from east. And that angle is 90 plus 45. 90 plus 45 is 135. So the wind angle, or the air, is moving at 135 degrees. I put that in my calculator, and I get an x component that's 418.0. I do the same thing with y components. Sine 30, sine 135, and I get when I add them that the y components add to be 253.3. So all I have to do now that I know x and y, I use the Pythagorean theorem to put them together. I'm going to write them over here. The x component is 418.0. The y component is 253.3. Notice they're both positive. Well, that means that the velocity is going to be in quadrant 1. Well, when I look at my picture, I certainly expect that this resultant will be in quadrant 1. So relative velocity all boils down to, can we add vectors? And we just need to make sure we are adding the correct vectors. That velocity comes out to be 490 kilometers per hour. So the wind actually causes it to go a little bit faster. However, it also blows it slightly off course. Got 31 degrees. So instead of sticking truly to 30 degrees, he's going to go at 31 degrees. If he does this too long, he's going to be off course if he hasn't corrected for the wind. In fact, we can do that. We can easily calculate how far off course he'll be if he doesn't adjust for the wind. Let's let's see what happens after 20 minutes. Well, assuming that the 450 kilometers at 30 degrees was his chosen course, that's where he wants to go. The only thing we have to look at to see how far off course he'll be is what did the wind do. So the distance from the wind is going to be 40 kilometers per hour. I need to multiply it by the time in hours. The time in hours will be 20 minutes over 60. That's going to be 1/3. And we can see after about 20 minutes, he's going to be about 13 kilometers rather, off course. All right, that concludes chapter 3. I hope you have good luck working all the problems.